So I think we've all mostly finally moved on to the next portion of 17B, which is talking about plotting stuff in 3 dimensions, and then very quickly moving on to vectors. So we'll talk about plotting in 3 dimensions for a bit, because it is something that's going to come back in 17C. So in 17C, there is going to be some expectation that you're able to figure out how to graph functions of 2 variables, learn about what their trace is. And I'm saying words that might not make sense yet. Find out what their trace or their level curves are. If someone says the word level curves, I want you all to think of a topographical map. Have you ever looked at a topographical map where there's like, like the little circles and you got like a little mountain and stuff? That's the whole idea with level curves. You're just saying, oh yeah, on this circle, everything is at the same elevation. On this other line, everything's at the same elevation. That's what a level curve is. Again, I know that's next quarter, but just preparing you all. Again, under the assumption that you all have to take 17C. I imagine there's some of you that don't, but that's not the assumption I'm operating under. Okay, let's talk about, sorry, I'm taking forever to write things down here. It is the 15th. 15th? See, I was talking about 17C so much, I was like, we've changed classes. Yeah. So let's talk about graphing in 3 dimensions. Let's turn the lights. This is all right. If you want me to turn off the lights, let me know. I will. I don't think I need to. So let's plot a point. Let's plot a couple points. Let's plot the point, say 2, 4, 6, which we're thinking of this in the usual sort of way, but instead of X, Y, it's now an X coordinate, a Y coordinate, and a Z coordinate for that 3rd dimension. There's a couple ways of drawing your coordinate axis system in 3 dimensions. I'll show you the 2 that I like. I'll show you the 2 that are standard. There are other ways of doing this, but here's one way. I like to draw first just your typical kind of 2D system, and then my 3rd dimension is going to be poking out at you. So here's the line that is poking out at you. And the way we typically orient this is your x-axis, this is your y-axis, and this is your z-axis. And I'm labeling the positive sides of each axis. So that's your positive x direction, your positive y direction, and your positive z direction. There's another way of doing this, which I'll mention in a second here, but this is the way I would usually draw it. It is important to get this like this because of how vectors work and how the right-hand rule works, which is something we're not going to talk about really, but this orientation does matter. If you like write X there and Y there and Z there, it's not actually really technically correct. So just be careful. Do it this way. So if I want to go 2, 4, 6, I'm going to go 1, 2 in the X direction, 1, 2, 3, 4 in the Y direction. Now be careful. I'm not going to end up right there. I'm going to end up right there. I'm essentially thinking of, right, I have a plane. The XY plane is kind of like the ground is what I'm thinking of really. And then from there, I'm going to go up 6. 2, 3, 4, 5, 6. I'm going to go up 6. Sorry, I have to like. So let me. Okay, I'm a liar if I try and do it that way. Here's what I'm really doing. I'm going to say I could go over 2 and over 4. I should say 2 in the X direction, 4 in the Y direction, or I could go 2 in the X direction and 6 in the Z direction, or I could go 4 in the Y direction and 6 in the Z direction, or 6 in the Z direction and 4 in the Y direction. I kind of just end up making a box. And that point right there is the one where I've gone 2 in the X direction, 4 in the Y direction, and 6 in the Z direction. But the order we did it in didn't actually matter, right? I could have gone 4 in the Y direction first, and then 6 in the Z direction, and then 2 in the X direction, as long as I'm doing the right number in each direction. So that's how I typically find where a point is in 3-dimensional space and try and look like it's about correct. But it really does take some imagination / visualization, right? You really have to look at it and be like, okay, I'm imagining going out towards you, and then these other things. I will definitely recommend In fact, I think it's relatively new. The Desmos /3D. You can do 3D graphing now in Desmos. I think it's worth looking at. It helps you see what's happening, especially next quarter when you start talking about more of this stuff. So I really, really recommend using that to be able to help you visualize what's happening. And just as a kind of another people like to do this, which is not the way I usually do it, but some people draw this more like this. They kind of draw 3 lines like this, which I should have spaced out a little bit better, but they think of this as being the X, this as being the Y, and this as being the Z. I'm not as big a fan of that, but if you happen to like that better, you can. My problem with this is I have a hard time in my head making the perspective be that that's a right angle. I know it's supposed to be, but it doesn't really look like it to me in the right way. So I don't know. I just don't like it as much. But you can do it this way and say, I'm going to go 1, 2 in the X direction, 1, 2, 3, 4 in the Y direction. Find where those meet. Again, when I draw these little dashed lines here, I'm always going parallel to the other axis. Right? When I drew this one here, I was going parallel to the X-axis, so I was moving in the X direction. And then I'm going to go 1, 2, 3, 4, 5, 6 in the Z direction, and then do the same sort of thing. I'm going to go up in the Z direction. I'm going to go over in the X direction to find that point there. I'm going to label these things all in just a minute here too. I'm going to go parallel to the Y-axis, parallel to the Z-axis, and finally, from here, parallel to the X-axis, from here, parallel to the Y-axis, from here up, see, it's okay-ish, parallel to the X. So there's your 2, 4, 6. We could also label these other points. Not that you normally have to do this, but I just want you to see them all. So, right, so that point right there is, 2, 0, 0, when I've gone just 2 in the X direction. Here's the point 2, 4, 0, 2 in the X, 4 in the Y. Here's the point 2, 0, 6, 2 in the X direction, 6 in the Z direction. Here's the point, let's see, I've gone in the Y direction and the Z direction, but not in the X, so that's 0, 4, 6. And I guess I could label this one as well. That is 0, 4, 0, and I could label that one as well. That's 0, 0, 6. Again, if I'm only trying to draw that point there, I'm not going to label all those other ones, but we certainly can to kind of see what's happening. Questions so far? Okay. Some language. Plotting points in 3 dimensions is about as useful as plotting points in 2 dimensions. It's something we can do, but like, why? I don't know, because just to practice knowing where things are, I think is really the reason why you would actually do that. But a couple of language things. So I don't know why I'm trying to leave that up there. It's not like anyone can see it. In 2 dimensions, sorry, I feel like yeah, that's fine. Fine. In 2 dimensions, we have 4 quadrants. Quadrant 1, where everything is positive. And then the other quadrants are counterclockwise. Quadrant 2, quadrant 3, quadrant 4. In 3 dimensions, we don't have 4 octants. We have 8, sorry, we don't have 4 quadrants. We have 8 octants. Each variable x, y, or z divides the plane, divides all of the 3-dimensional volume in half. And so what's happening here is x, y, z. This kind of one that's the closest to us over here, where x, y, and z are positive. This, oh wow, geez, James, come on. This space here, that is your first octant. The first octant is where, again, just like the first quadrant was where both x and y are positive, the first octant is where x, y, and z are all positive. and there aren't names for the other octants, or at least not that I've ever heard. I don't know how you would decide to order which name got which thing. I don't know which one is octant 2. It's probably that one or that one or that one, but like I don't really know. And I don't think anyone actually knows is the real answer here. There is no typical labeling or talking about octant 2 or octant 3 or octant 4. If I was going to describe a different octant, I would say I want the octant where X is positive and Y is positive and Z is negative to describe the one down there. That's how we would do it. We wouldn't try to be like octant 7. Okay. Cool. The reason I mention this is because a lot of times people describe a thing as we want this space or surface or whatever that is in octant 1. Just like oftentimes in 2 dimensions, we say, I want to look at the area bounded by this curve that happens to be in the first quadrant. So that's why we're talking about this octant, because it's a usual way of describing where stuff is. I might kind of think of this about like a 2x2 cube, a 2x2x2 cube, not a 2x2, right? If we think of this as like a 2x2x2 cube, we think of each of the smaller cubes, it's like a terrible dumb Rubik's cube, right? Like not like a 3x3 one that's actually hard. I mean, I'm sure 2x2 one would not be easy for me personally because I've never spent my time doing Rubik's cubes. But how many cubes are there in this 2x2x2 cube? I should say, how many smaller cubes are there? Let's see, there's 1, 2, 3, 4, 5, 6, 7, and there's one back there we can't see. So there's 8. 2 times 2 times 2. And this one here, that's your first octant. And then there's the 1, 2, 3, 4, 5, 6, 7 other octants. So you can kind of think of them as like rooms stacked on each other. You've got this cube here, there's your first octant, and this cube over here, this cube back here, this cube back here, and then 4 underneath as well. It's kind of like a small house with 8 rooms. Or like, I would go Lego. I should have bought Legos. That'd be great. You did like 8 little Legos stacked on each other. Okay, so that's what we're dealing with. Some other stuff to be aware of when we start talking about graphing in 3 dimensions is what the planes are. So I might frequently, and this is not great for the people on Zoom, but I'm going to say it anyway because it's useful. I like to think of this. So for the people in Zoom, look at a corner in your room. Like you're looking ahead, look like to the corner that's like left to your left and ahead. That corner there. I'm going to think of that corner over there as the origin. And then that edge is the x-axis pointing out towards you. That edge is the y-axis pointing left to right. And this edge is the z-axis pointing up to down. And so we're all living in octant 1. Right? We are in the first octant because we're in the octant where everything is positive. And then the hallway out there would be where y is negative. And the room over there would be where x is negative. And the room and the room above us would be more positive for z. The room below us, and there are rooms below us, would be where z is negative. Kind of makes sense. For the people on Zoom, that makes not much sense. You come to class and do it. Yeah. All right. So what I want to point out is sometimes we talk about the different what is the word I'm looking for? We talk about the different planes. So there's 3 important planes. I mean, there's many important planes, but there's 3 we want to talk about. So the XY plane. I'm going to draw it. Here's my usual XYZ coordinate system. The XY plane is the same as it ever was. It's all the stuff in the XY plane. So meaning we're looking, and we have to kind of pick just a boundary here. And there's the XY plane. Or in terms of the room, the XY plane is the floor. And then we have, so XY plane, the floor. And then we have the YZ plane. So in the XY plane, what's true about, sorry, I got to hit myself there. In the XY plane, you haven't gone up, you haven't gone down, so Z has to equal 0. So if we're talking about the XY plane, Z is 0. And that is literally the equation of the XY plane. And now in a similar way, the YZ plane, which I'm going to think of as the wall you're looking at. It doesn't sound nearly as poetic as the floor. Is this plane over here. And it's the plane where x equals 0. We haven't moved forwards or backwards. So it's everything that's just sitting on this wall up here. Nothing out towards you, nothing away from you. And finally, I think you all know what the last one's going to be. Notice when I draw these rectangles, I do draw the lines so they're parallel to the other axes. It just looks better. So here is my XZ plane, where y is equal to 0. And again, if you're imagining things in the room we're sitting in, it's the wall to your left. It's kind of giant. All right. Sometimes we have to graph things in 3 dimensions that are not too terrible. We should talk about how they work. And the thing I'm going to start off by saying most of all is, if you're missing a variable like x or y or z in your equation, it usually means that value can be anything. Here's what I mean by that. If I was going to graph, in fact, all of you should graph in 2 dimensions, y equal to 6. Give you a moment here to graph it. Take my pens. There's the line y equals 6. Okay, but importantly, on the line y equals 6, what does x get to be? Anything, everything, right? So if you have an equation that doesn't include a variable, that variable gets to have free range and be whatever it wants to be. It can be as big as it wants. It can be as negatively big as it wants, anywhere you like. The same thing is going to be true when we start graphing equations that have x, y, and z. If you're missing a variable, you essentially get to extend the graph in that direction forever. So let's look at some examples. Let's say I want to graph. We'll graph some planes first. In fact, let's take that same equation and now graph it in 3 dimensions. So graph the plane y equal to 6. Okay, well, if y is equal to 6, that means x gets to be whatever we want, or not whatever we want. It really should say anything, and z also gets to be anything. So the only constriction here is that y has to equal -6. So there's my x, y, z coordinate system, which we typically don't label unless we feel like there's a good reason to. And let's say that y equals 6 is over here. There's 6. I can zoom in. A little bit easier to see what's happening here. And then I'm going to extend this point in any of the free directions. So I'm free to move in the z direction as much as I want. I'm free to move in the x direction, and I have to be kind of careful drawing this here, as much as I want. And what I really have here is a plane. I'm trying to draw nicely here. There's a plane that is just moved 6 to the right from the xz plane. So y equals 6 is just the xz plane, but it's moved 6 to the right. Oh, sorry, can you see that? Not quite. So if you don't have a variable, right, you just get to be like, oh yeah, that variable, we can move as much as you want in that direction. The thing here is typically when you have like just y equals something or just equals something or just x equals something, you have 2 degrees of freedom to move in. you can move, in this case, up or down or forwards or backwards. Or if I wanted to say draw the plane, let's graph the plane z equal to 4. Well, same idea. Now we're setting the z value, and x and y can be anything. Wow. Trying to draw straight lines. I can't tell you how jealous I am of all you with your notepads, like be students, and you can just draw like a perfect straight line whenever you want. So jealous. I know it doesn't seem like a big deal, but I feel like the oldest man ever saying these words right now, but I am jealous. It's cool. I wish I had all that when I was a student. Anyway, enough of me being old. So there's z equals 4. And again, right, we can't go up or down because z has to be 4, but we can go left or right or forwards or backwards. So we're going to extend this in the, and so I like drawing these lines that go through the point in the directions that we're allowed to move in. But really you're trying to draw like the square or rectangle that contains that stuff. So really what I'm really doing is saying, okay, from here, I'm then going to also draw another line parallel to the y-axis, and over here also another line parallel to the y-axis. And then here I'm going to try and draw lines parallel to the x-axis. Try not to draw on the actual x-axis because then things just look weird. And then same deal over here. And then there I would kind of fill it in, be like, all right, there's my z equal to 6. Sorry, 4. Apologies. Do your best, and it does take practice. You're looking for this water bottle, maybe? Yeah. Thank you. You're welcome, of course. Everything you're not the only one. Another water bottle of fun and a jar of honey. So I'm glad everybody got the stuff. All right, so try to do your best, especially if you're moving in the x direction, to draw your lines parallel to the x direction. That's always going to be the hardest one for me because it's always going to be kind of slanty. Whereas the other two, the y direction and the z direction, should be very much just your usual perpendicular, typical axis setup. And then you can make your x direction, you can make it more shallow or more steeply towards you. It just depends on how you like to visualize that third dimension. And it does take practice, years of practice, and you might not suck. I'm sorry, years of practice, and I might not suck. You might all be great drawers. I am not a great drawer. You've obviously seen much evidence of that. If you practice enough, you might get good at drawing some of the math stuff if you're me. And then finally, oh yeah. So let's talk about if we actually, so let's say we wanted to graph, and this is where things get kind of annoying. Let's say I wanted to graph the equation x equals, sorry, not x equals, geez, James, come on. Y equals 6 and z equals 4. We've already kind of graphed both of them, but now for both of these things to be true, we have to be graphing essentially, or we only have freedom in the x direction. So we're essentially taking where this plane and where this plane would intersect each other. Because on that line of intersection, both z is 4, y is 6, and x still gets to be whatever you want. So let's see, I really don't want to draw it again, but I will. Can I make it fit? I can make it fit. So here's z equal to 6. And I'll just draw it a little bit more easily here. Oh, come on. So there's z equal to 6. And over here, maybe here, it's parallel here. There's y equal to 4. And this line, sorry, I should label things here. Labeling is important. And then this line here, that is your line of intersection. That is y equal to 6 and z equal to 4. Question. Oh, because I'm dumb. Sorry, because I wasn't paying. No, not sorry, because I'm good. So I'm really good in it. So sorry. I meant for that to be z equal to 4 and y equal to 6. If you guys should just shout out, James, you're doing the wrong numbers. Because sometimes I interchange numbers. Yeah, sorry about that. Yes, it should be normal. There's nothing weird, funky going on here. Things should act as we expect them to. So if some numbers seem to magically transform, it's because I've accidentally transformed them. It's clearly in my mind 4 and 6 are the same number. Not really, but you know. So two planes intersect in a line if they intersect. The two planes could be parallel, so that'd be weird. That's not really describing a graph. Let's continue on with some other surfaces. This is a surface, right? I think of a surface like I kind of think of a blanket. Sometimes it might be like you're laying under the blanket. It's kind of like this, like a wave, maybe, or like the surface of the ocean, right? The surface, the top of the ocean, could be flat like a plane, or it could be kind of undulating, or it could be really wild if there's waves and stuff, right? But these surfaces were eventually, again, in 17C, we eventually are going to talk about finding the volume under a surface over some region, which is why we're talking about this stuff. Okay, so let's look at some not terrible surfaces. Pens. So let's look at, let me back up just a tiny bit. And let's say we want to graph x squared plus y squared equal to 9. And in 2 dimensions, the graph of this would look like what sort of favorite shape? Not a parabola. Oh, it's been a while. This in 2 dimensions is a circle. Center is the origin. And the radius is the square root of 9, which is 3. Right, x squared plus y squared equal to a number is a circle. Or if you have x minus 5 squared plus y minus 2 squared, the center is 5, 2. But in 3 dimensions, well, we're going to graph a circle, but what variable is missing in 3 dimensions? X, y, or we're missing z, meaning that we're going to draw a circle in 2 dimensions on the floor, on the xy plane, and then we're going to extend it in the missing dimensions direction. It's not hard to draw. It's kind of hard sometimes to wrap your mind around. Not hard to draw, he says, before he draws it. Maybe I should have drawn it first. So here's my XYZ coordinate system. So I'm going to draw a circle of radius 3, but it's going to be in the XY plane. So it's not going to look like a circle. It's going to look like a circle that I've drawn on the flat ground. So this is where your sense of perspective has to kind of play a role here. So what I would point out is if you're trying to like do things by making little notches, it can be challenging. But the X notches shouldn't be as far apart as the Y and Z notches, because right, you've taken something that's this long in the Y or the Z direction, and then you have tilted it, and it doesn't look as long anymore. If you look at it like head on, right? It looks much shorter. So the X notches should be shorter or closer together than the Y and the Z notches. So I'm trying to draw a circle going through those points there. Great, there's my circle in the XY plane. And now we're going to extend it in the Z direction. And I wouldn't try and draw it again. I wouldn't try and like draw points again. I'd be like, well, I'm just going to draw another circle like that. And we have a cylinder. So I'm going to be a little bit more specific because, yeah, we have a circular cylinder. You might ask, James, aren't all cylinders circular? And my answer is no, they're not. Cylinder is a word that we often think of as being like something that looks like a pipe, but actually a cylinder, the definition mathematically is far more generic, which we'll talk about in a second here. Let's look at another example. So that's how we graph it. And again, I don't really, my graphing skills, I don't really want to try to shade this in, but right, we've just got this. And really, I should point out, it extends both in the up direction and in the down direction. There's our circular cylinder. Let's graph the following. Let's graph, I like that one, sure. Let's graph z equal to x squared. X squared, sure, why not? Plus 1. All right, what variable is missing? Y. So we're gonna have to graph this. Now it's a parabola. We're gonna have to graph that parabola and then extend it in the y direction. So it's gonna kind of look, in fact, this is where I think having a physical thing, it's gonna really look like you took a parabola and extended it in the y direction. It's gonna look like a sheet of paper that's a parabola. That's it. That's a much better visualization than I'm going to be able to draw, but I'm still gonna draw it. So graphing this, first I'm gonna graph just in the x, z plane, the parabola z equal to x squared plus 1. So I'm going to go up 1 and then graph the parabola. But again, be careful. In fact, I'm not going to graph like your head-on parabola, right? Because it's in the plane that's kind of slicing towards you. So I'm trying to draw a parabola on this wall, but then look at it from this perspective. Oh, it doesn't look like your full-on nice symmetric parabola. It looks like it's been tilted. So that's how you have to try and draw it. That's, to me, for me, that is the hardest part of this 3D graphing stuff, is just trying to make things look like they make sense perspective-wise. This is when would have been good to have taken some art classes in high school or college, but I didn't. So, you know, there you go. I think drafting. I was okay at drafting, kind of. And yeah, that's probably, this probably should be, I would probably make that go a little bit higher up. So I'm kind of imagining, right, those points there as being at the same z height, because they are on the same line that is parallel to the x-axis. Another way to think about this is these are both coming from, like, that could be x equal to 3, and that could be x equal to -3. And so the z values are the same. And then we're going to extend this thing in the y direction. So what I'm really going to do is I'm just going to try and draw horizontal lines that are the same length, and then draw another parabola that goes through those. It's not a perfect process, but it worked okay this time. So there's your parabolic, your parabolic what? Your parabolic cylinder. Because we call this a cylinder too, because mathematicians like to use the same word over and over again for things. So this is a quote unquote parabolic cylinder. For the most part, if you take any two-dimensional curve other than like a straight line and extend it in a third direction, we call it a, whatever kind of curve you had, cylinder. So if you took an oval and extended it into a third direction, you call it you probably just call it a cylinder, an oval, I don't know. If I took a hyperbola and extended it in the third direction, we called it a hyperbolic cylinder. Gross. And I'd have a hard time drawing it, maybe. Observations, comments, questions so far? Yeah. No, it's not at all like parametric equations. Definitely not. We don't really, I think, ever get into parametric equations. I don't think we ever, I don't believe we ever get into parametric equations in 17B or C, I think. Unless your teacher is talking about them, and then you are. Okay, all right. All right. Yeah, in fact, so let's do one more. Let's graph. Yeah, let's do, ooh boy, geez, James, you really want to do that to yourself? No, I really don't. Let's graph this. Yeah, fine. Let's graph z equal to 1 over y with the condition that y is greater than 0. Oh, sorry. One thing I like about graphing things when the x is missing is at least I can start off in the plane I'm used to drawing things in. Right? If I think about this, I'm going to start off drawing in the XY plane. Oh my gosh, James, the Y, holy smokes, the YZ plane, which is your usual like head-on typical graphing situation. So I'm going to graph Z equal to 1 over Y. Yeah. And so it's going to look like this. There's my Z equals 1 over Y. And I didn't want to graph this part over here because I felt like it was going to be too hard to extend it, but I might try to. So now let's add in the Z axis. And then we're going to try and extend this in the Z direction. So again, all I'm really trying to do is I'm trying to move this down in the Z direction. So I might take that point there, which is 1, 1. And I might try going down here and say, okay, if I go over 1 and up 1, and then I've kind of got like a vertical asymptote kind of deal here. It's really like a planar vertical asymptote. You've got a whole plane that's an asymptote. Seems strange, I know. We're kind of trying to do this. And then we're saying we've got kind of, oops, so look at that. I didn't do a good job because I didn't draw that parallel to the axis of movement. That was a bad choice on my part. I should have drawn it more like that. That would have been better. Same deal here. I should try and draw that parallel like that. It kind of looks like a slide. Kind of. Okay, and we would call this is a hyperbolic, because Z equals 1 over Y is a hyperbola, hyperbolic cylinder. Or at least half of one. Because I didn't draw the other half because I thought it was. I didn't draw the other half because I knew that this part was going to cover up the other half and it was going to look really messy. So yeah. Again, I would encourage all of you to go graph Z equals 1 over Y on Desmos 3D and then spin it around and see how it looks. I think it is actually worth your time. Okay, let's graph a few more time. Okay, yeah, let's graph. So tomorrow, the next day of class. Whenever, if I say tomorrow in class, you know I'm in the next day of class. Maybe you don't. It's okay. So let's graph something like Z equal to Y, which I feel like becomes problematic because of perspective. So here's what I mean. I know Z equals Y looks like this line here. I don't want to draw my x-axis so it's exactly looking like that. So I'm going to try and draw my x-axis like extra shallow here. Maybe like that. So there's my x-axis. There's my y-axis. And then Z equal to Y. And let's use a different color here because why not? Z equal to Y looks like that line right there. But it's not just that line, it's that line. And then I'm going to extend that line in the x direction. So I'm just going to move this in the x direction. So I'm going to try it. And this is where having a ruler is a really good thing to have, probably. Let's take my ruler here, slide it along so my line looks parallel to how it did before. I can even measure if I wanted to measure. So like, okay, I went from 4, that's almost exactly 4 centimeters. So I'm going to slide it along here so it's parallel. Then try and draw it again exactly 4 centimeters. Oh, that's pretty smart, James. There's your plane. What does that plane actually look like? Well, planes are just pieces of paper. I take a piece of paper and here's my graph. Here's what it looks like in the usual orientation, right? I've got Y equals Z, and then it's moving out at you in the X direction. You guys see that on Zoom too. Right, Y equals Z, usual like Y equals X kind of shape, and then moving out at you. It'd be kind of like if I had a giant curtain that started at the bottom of the edge there, and I drew the curtain all the way up to the upper edge there. That curtain or blanket or whatever would be the plane Z equal to Y. A lot of this is really using your imagination. You have to actually try to imagine how this stuff looks because, well, actually, I should say, you all have the benefit of technology, right? You can also use Desmos or GeoGebra to actually really kind of see how these things look. But you still have to try working your imagination. I'd say it's going to be true if you have to like do, because you'll probably have something. Yeah, probably. You might have some small amount of this three-dimensional graphing stuff questions on your final exam. Probably not, to be honest. Like I wouldn't bet on that, but it's not an impossibility. There was one other thing I wanted to mention here. I mean, okay, one other thing. There's always one more thing. But yeah, let's talk about spheres, circles, and spheres. So the equation of a circle. So the equation of a circle, let's write the general equation with center h comma k and radius r is given by x minus h squared plus y minus k squared equal to r squared. And the reason that is the equation of the circle is because literally, if you draw a circle with a center of h comma k and a radius of r, and I ask you, well, everybody, how do you describe the points on the circle? Well, every point on the circle is the same distance from the center. Okay, great. I know the distance equation, so do you. The distance from that point to that point, it's the square root of the difference in the x coordinates squared plus the difference in the y coordinates squared. And it's equal to whatever the value of the distance actually is, which we're calling the radius. And then if you square both sides, you exactly end up with your equation of the circle. So really the equation of the circle is just a result of the distance formula. So square both sides and you exactly get the thing we already wrote. The same thing is true for the equation of a sphere. We'll try to not move too much here. So yeah, I can draw. I think I can. Maybe I can fit all the things all at once here. So drawing a sphere, you just draw a circle and then you kind of make it look like it's got 3 dimensions. So there's my center, which I'm going to call h comma k comma j. I think j is the standard choice there. And the radius of my sphere is also r. And how am I going to describe any point on the sphere? Well, just like before, the distance between any point on the sphere, any point x, y, z, and the center, h comma k comma j, is r. Or in more mathematical terms, the distance is the square root. Okay, so here's the nice thing about the distance formula in 3 dimensions. It's the same as the distance formula in 2 dimensions. You're just adding on a third piece. So it's going to be the difference in the x's squared plus the difference in the y's squared plus the difference in the z's squared. And that's going to equal r. And then we square both sides. And we get the equation is x minus h squared plus y minus k squared plus z minus j squared equal to r squared. So that's the equation of a sphere whose center is hkj and radius is r. Very similar to the circle equation, just with an extra piece. So some typical examples would be something like, oops, sorry. For example, x squared plus y squared plus z squared equal to 36 is a sphere. Is a word I feel like I don't say particularly well. I feel like I'm saying too much F, sphere, I don't know. It's not my favorite word to pronounce. It's a ball. Oh, it's actually, the ball is a ball is a filled-in sphere. So someone says ball, they actually mean the interior of the sphere as well as the surface. So I shouldn't say ball. Is a sphere with what center? Oh, what is the center here? Good question. When I think about the center of a circle or a sphere, I think about the values of x, y, and z that make the left side equal to 0. So here, what would x, y, and z all have to be so that the left side was 0? It's not a trick question. They're all 0. That is the only choice. The center here is 0, 0, 0. Like I say all the time, the center is not a point on the sphere. If you plug in 0, 0, 0, does 0 squared plus 0 squared plus 0 squared equal 36? Of course not. So the center is an important point, but it's not actually a point that satisfies the equation of the sphere because it's not a point on the sphere. It's totally fine. The radius is the square root of 36, which is 6. Yes, it's still a square root. It's not like a cube root or some other weird power because we have an extra dimension. It's still a square root. And if you tried to draw this, if I tried to draw it accurately, I would probably do this. I would say, here's my 6, here's my 6. So 0, 0, 6, 0, 0, negative 6. I probably wouldn't actually label it. And then I would try and draw the circle in the YZ plane. And then I would try and draw the circle in the XY plane. And I probably wouldn't draw the circle in the XZ plane. I'd be like, that's good enough. That looks like a sphere. I think we can all believe that's a sphere. Maybe. Let's look at, we got time for squeeze one more thing in. Yeah. So let's look at this example because this is actually, I think there's a question like this on some people's homework assignments. Let's find the center and radius of the sphere given by the equation x squared plus y squared plus z squared plus 8x minus 6y plus 2z plus 17 equal to 0. And here's what I want you to see. That does not look like the standard equation. Sorry, the standard equation of a sphere. It's certainly a sphere, and we know it's a sphere because we have x squared plus y squared plus z squared and lower powers of x, y, and z. And they all, x squared, y squared, and z squared all have the same coefficient. It's not something you need to know so much now, but again, I do think it comes up in 17C. So we know we have a sphere if we have all x squared, y squared, z squared having the same coefficient. If they had different coefficients, like it was x squared plus 2z squared plus 3y squared or whatever, you'd have like an ellipsoid, which is like an oval, but with 3 dimensions. So what do? Well, just like when you were trying to find the equation of a circle and you had an equation like this, you have to complete the square. So we're going to take x squared plus 8x and leave yourself a space to complete the square. And then y squared minus 6y and leave yourself a space. And then z squared plus 2z, leave yourself a space. And I'm going to bring the 17 over to the other side. So that's going to be a negative 17. And then I'm going to add on the same 3 things on the right that I'm adding on the left. I think this is a really good starting place for this process. Okay. How do we complete the square? You take the coefficient of x to the first or y or whatever, whichever one we're looking at. You take that 8, you divide it by 2, and you square it. You're going to get 4 squared, which is 16. If you add it to the left, you have to add it to the right. Same deal here. Take your negative 6, divided by 2, square it. Negative 3 squared is positive 9. You're always adding a positive number. You were never adding a negative number when you're completing the square. And then lastly, z squared plus 2z, 2z, 2 divided by 2 is 1. 1 squared is still 1. Why did we complete the square? Because when you complete the square, This whole thing factors now. This whole piece factors as x plus 4 squared. This whole piece factors as y plus 3 or minus 3? Minus 3. And it's got to be a minus 3 because you do y minus 3 squared, you get y minus 3 times y minus 3, and you need a negative 6y in the middle here. So if this sign is negative here, that sign has to be negative there. If the sign is positive here, that has to be positive there. And lastly, we have z plus 1 squared equal to negative 17 plus 16 is negative 1, plus 9 is 8, plus 1 is 9. So my center, again, just like before, I'm thinking about the XYZ coordinate that makes the entire left-hand side equal to 0. That's going to be x has to be negative 4, y has to be positive 3, z has to be negative 1. And my radius is the square root of 9, which is 3. And that's the center and radius. So to find the center and radius of a sphere, you write it in the standard form like this, and then you just read the things from the equation. Cool. I'll see you on Friday.